So guys, in this chapter we are extensively going to deal with various operations that are to be performed on matrices. So let's start with our first topic, that is elementary transformations. Now, elementary transformations are defined as set of operations performed completely on a row or a column of a matrix so as to generate a matrix equivalent to the original one. Now, the word to be noted is equivalent. That is, the generated matrix after the operations are performed are not equal but are equivalent. Now, to explain this word equivalent, let me take an example. Let us say there is an equation 3x is equal to 6 and 9x equal to 18. Now, both these equations give the value x equal to 2. This does not mean that both these equations are equal. They are equivalent as they produce same effect on the value of x, that is x equal to 2. So, after performing all these operations on the matrix, the generated matrix will always be equivalent to the original one, and this equivalence will be denoted by the symbol. So, now another point to be noted is the operations are performed completely on a row or a column, and they are not performed on elements of the matrix singularly. That is, any operation to be performed on a matrix A, B, C, D should either be row wise or column wise and not on a single element. So, let us continue. The very first operation is interchanging the row by a row or a column by a column. Suppose these transformations are denoted by Ri, Rj for rows and Ci, Cj for columns, where I and j represent the number of the column or the row. So let's take an example. Suppose A be a matrix 9, 7, 6, 4. So suppose this is the row 1, this is row 2. We need to interchange these rows. So the operation will be denoted as, and the matrix will be written 6, 4, 9, 7. Now note, this matrix is equivalent to the original matrix A and not equal, hence this symbol is shown for showing the equivalence. Let's take another example. 4, 3, 2, 1. Here we need to interchange columns. So this interchanging will be shown by, and equivalent matrix will be written as 3, 1, 4, 2. Here the row 1 is exchanged by row 2 and vice versa. That is, the 6, 4 is the first row and 9, 7 is the second row. Here column transformation has taken place. That is, 3, 1 has become the first column here and 4, 2 has become the second column. So this is the first elementary transformation that we are learning, that is interchanging a row by a row or a column by a column. We have learned the first elementary transformation, that is interchanging of two rows or two columns. Now let us move on to the second elementary transformation of matrices, that is multiplication of elements of any row or a column by a non-zero scalar. Now let k be any non-zero scalar. Now if we need to multiply this k across a row, then the operation will be written as R1. Suppose, let's say this k needs to be multiplied across first row. So R1 gets transformed to K R1, and the equivalent A will be written as KA, KB, C, D. Now, if we need to multiply this K across a column, then suppose, let's say we multiply this K across column C1. So C1 gets transformed to KC1, and every element of the column 1 will be multiplied by the K. Therefore, the equivalent A matrix will be KA, KC, B, D. So, in general, if we need to multiply any row Ri by any non-zero scalar, then it will be represented as Ri gets transformed to Kri, and each element of the respective row will be multiplied by K. Similarly, for a column, if we need to multiply ith column by K, then it will be represented as Ci gets transformed to KCi, and each element of the respective column gets multiplied by K. So let's move on to the third elementary transformation, that is adding scalar multiples of elements of a particular row or a column to corresponding elements of other row or a column respectively. Now, let A be a matrix A, B, C, D. In the earlier example, we had learned multiplying a scalar to completely to a row or completely to a column. Now suppose we take row 1 and we need an equivalent matrix something like this: A plus KC, B plus KD, C, D. In the earlier example, if we multiply a scalar to a particular row, then its elements get changed to KC and KD. But here observe that this C and D remains the same, but its scalar multiple is being added to the first row. So, how does this elementary transformation take place? So, this elementary transformation can be written as R1 transforms to R1 plus K R2. Here, even though the K is multiplied with R2, but it does not change R2 because we are not transforming R2, but with the help of multiplying the scalar to a row R2, we are adding that multiplied row to R1. Hence, the row R2 remains same. Similarly, if we need to alter C1 in a similar way, therefore it can be written as C1 plus KC2. C2 will not be altered, but the resultant matrix will be A plus KB, C plus KD, B and D. So, in general, adding a scalar multiple of element to particular row or a column to corresponding elements of other row and a column respectively can be represented as Ri is equals to Ri plus KRJ. Note that this Rj doesn't change. It remains as the same of the original matrix, but the change occurs only in Ri. Similarly, in the case of Ci, is Ci plus K Cj. Here Cj doesn't change, the change only occurs in Ci. Here are some important points that we need to keep in mind for this third type of elementary transformation. The first point is, in operation Ri which gets transformed to Ri plus Krj, or Ci which gets transformed to Ci plus Kcj, the term Cj and Rj remains same as that of original matrix. That is, if there is a matrix A, B, C, D, and as said earlier, if we want to add the scalar multiples of this to Ri, the effect only gets to Ri, whereas the C or R2 remains same. The elementary transformation from a row can't be applied to a column and vice versa. That is, a row can't be interchanged with column. That is, this cannot be written as AB can't be made column and BD will remain same. This means there is some mistake as C goes missing if we interchange a row with a column or do vice versa. Hence we get a wrong matrix. And also in elementary transformation of Ri which gets transformed to Ri plus Krj and Ci which gets transformed to Ci plus Kcj, the coefficient of Ri and Ci must always be 1. That is, you have already observed that here the coefficient is 1. We cannot multiply the row which needs to be transformed by any other multiplication while adding the scalar multiples of other row or column respectively.